everyone. Really excited to be kicking off our afternoon session here on detecting and responding to methane leaks. I feel like in the morning sessions, we've been hinting at and talking about this really important topic. And so now we have a whole panel of experts to really dive in. So I'm Morgan Edwards. I am an assistant professor of climate policy here at UW-Madison and one of the co-chairs of the conference. I'll also be moderating this session and have special interest in methane policy. So we're going to have each of our panelists who can speak for 15 minutes, and then they'll all come up and we'll do a Q&A with the audience. So first off, we have Daniel Varon, who is a postdoctoral research fellow at Harvard University. Then we have John Goldstein, Senior Director of Regulatory and Legislative Affairs at the Environmental Defense Fund. And finally, Ángel Esparza, who is a Principal Technical and Policy Advisor at GHGSat.
So I want to start us off with a sort of high-level overview of satellite observations of atmospheric methane and the different capabilities for quantifying emissions across scales. The background context for this work is that atmospheric methane has recently become a major focus of both science and policy. On the science side, there's been a long-standing debate over what is driving recent methane trends. You can see over the last 4 decades, methane has been increasing in the atmosphere in fits and starts. And this could be due to changes in emissions, like from wetlands or potentially from oil and gas development, or it could be due to changes in the primary sink of methane in the atmosphere, which is the hydroxyl radical, OH. And this is still not fully understood. Now, at the same time, on the policy side, methane has been identified as the best lever to control near-term climate change. And that's because it's a potent greenhouse gas responsible for about 30% of the warming experience so far. And unlike CO2, it's got a relatively short atmospheric lifetime of about 10 years. And that means that if we cut emissions today, we'll see benefits almost immediately. Now, it needs to be said that this is not a substitute for cutting CO2 emissions, because by the same logic, over a 100-year time scale, it's the longer-lived gas that's more important. But if we're going to keep below our 2-degree temperature targets for the century, we really need to go after methane immediately. And this has become particularly pressing in the last couple of years when we've seen an uptick in the growth rate. So 2020 and 2021 both set consecutive records for methane growth, and we still don't fully know why. For all these reasons, there's been a strong need for better understanding of methane emissions. But it turns out this is a really hard problem because methane comes from a wide variety of different sources, natural and anthropogenic. On the natural side, the dominant source is wetlands, but there are smaller emissions from sources like geological seeps and termites. The anthropogenic emissions come from a wider array of sources, livestock, oil and natural gas, coal mining, waste management, so on. And to make matters worse, these anthropogenic emissions come from a huge number of point sources that are scattered all around the world. So things like coal mines. This is a ventilation shaft for a coal mine in New Mexico, or cattle feedlots, landfills in cities, or oil and gas facilities like these well pads in the Uinta Basin. All of these are important. And so there's been a lot of interest in using satellites to monitor emissions across these scales, from the level of individual facilities all the way up to global sectoral totals. And this is the satellite observing system for methane. The underlying instruments are currently active, and the others are still to come. And it comprises a suite of area flux mappers up here, which are instruments designed for global and regional scale monitoring of emissions, and also point source imagers, which can zoom into high resolution and resolve individual point source plumes. So first of all, how do these instruments work? Well, there are 2 strategies for satellite remote sensing of methane. One is to observe in the shortwave infrared, which means observing backscattered sunlight. The other is to look in the thermal infrared, which is light emitted directly from the Earth. And these 2 approaches give very different information about atmospheric methane. In the thermal infrared, you're mainly sensitive to methane in the upper atmosphere, and you have almost no sensitivity near the surface. So for these instruments that are interested in quantifying emissions, they all use the shortwave infrared, which gives near uniform sensitivity over the atmospheric column. Now, within the shortwave, there are 2 more options. So this is showing optical depth, which is a measure of absorption by different trace gases in the shortwave infrared part of the spectrum. You can see that for methane, there are 2 peaks. One is at 1600 nanometers and one's at 2300. The benefit of observing near 1600 nanometers is that you can also get CO2 at the same time. But if you look at the 2300 nanometer band, the absorption is stronger. So there's a higher signal. And these instruments all use one or both of those bands. Okay, so now let's compare them in terms of the magnitude and spatial scale of emissions they can quantify. Start with the oldest one, GHGSat, which we've had since 2009. GHGSat has global coverage, but relatively coarse spatial resolution. So it mainly provides information on emissions at continental scales. In 2017, we got a game changer in Tropomi, which, like GHGSat, has global coverage, but has much finer spatial resolution, down to about 5 by 7 square kilometers. And also it has daily observations around the world. And so this has gotten us down to the regional scale, for example, of individual oil and gas basins like the Permian Basin in Texas and New Mexico, which we can see here in a month of Tropomi observations, and very clear hotspots from the Delaware subbasin in the west and the Midland subbasin over here in the east, which are the kind of areas of the most oil and gas production. Now, what Tropomi can't do is resolve the individual point sources and facility level emissions that are giving rise to these regional hotspots. And that's been the domain of the point source imagers, and particularly the ones circled here are targeting instruments. It started in 2016 with GHGSat. So these instruments don't have global coverage, but they can zoom into individual areas of interest at very high resolution, down to about 30 meters, and pinpoint individual point sources at the facility scale, like from oil and gas facilities in Permian or coal mines in Australia. And so what this has done is given a way to directly identify opportunities to reduce emissions at the facility scale and generate actionable information for operators and regulators to mitigate emissions. Now, there's been a recent development in this, which is the realization that global surveying instruments like Sentinel-2 and Landsat, surprisingly, also have capabilities for mapping methane point sources. And that's because, as we showed in a paper last year, they happen to have spectral bands that are very well aligned with methane's absorption features in the shortwave infrared. And so we showed that we can combine these bands in different ways to map methane point sources, if they're strong enough, down to 20-meter resolution globally every few days. And the Landsat record goes back to the 1980s. So this is just a gigantic new historical data set that we still need to mine. Okay, so all this development has been extremely rapid. It's been over the last 5 to 7 years. And you can see there's all these other instruments that are coming down the line. They'll have their own strength capabilities. And I think we'll hear about some of them later in the session. But what I want to do now is look at some examples of how we can use the current observing system to monitor methane emissions across scales. And starting at the global scale of Tropomi, this is showing 1 year of Tropomi observations around the world for 2019. So more than 50 million observations went into this plot. The data set is extraordinarily dense, and there's all these patterns that arise, kind of ask us to investigate. Some clear ones, of course, are these hotspots in China and India, but there are also smaller hotspots around the world over areas of oil and gas production, like Western Turkmenistan, Nigeria, and the Permian Basin. And so I want to look at a couple of these. I'll look at Western Turkmenistan and the Permian Basin for examples of how we can monitor oil and gas methane emissions with satellites, starting with Western Turkmenistan. In 2019, the GHGSat and Tropomi teams started monitoring a major hotspot from the Korpeja oil and gas field in Western Turkmenistan. And it was initially GHGSat who discovered these massive methane plumes in the area, primarily coming from a compressor station, which is hidden beneath the large plume on the left of that bottom plot there. And over an 11-month period, they detected huge emissions from this compressor station 7 times, averaging about 27 tons of methane per hour, which, to put in perspective, is comparable to some of the worst historical methane releases from oil and gas infrastructure in history. So this was a pretty big deal, and the Tropomi team hopped on it as well. And with their daily global data, they were able to detect anomalous emissions here on 128 passes over a similar 14-month period. And they estimate on average 60 tons per hour, which would indicate more point sources in that regional enhancement, which the GHGSat panel down there is kind of exemplifying. So in a follow-up study, we used Sentinel-2 to look at the history of this source. We went back to August 2015, and we detected another 68 plumes on average with a pass every 5 days. So the emissions on average were about 20 tons per hour with good agreement with, during the GHGSat study period. But what I really want to draw your attention to is this period here. After GHGSat got in touch with the operators through diplomatic channels, the emissions stopped. So we know that because these lines on the bottom of the plot are showing detections and non-detections, and there's a lot of red here. So it's just clear seams with no plume for about 9 months. And then, of course, okay, the emissions started again. So that's not great, at a really, really high rate. And since then, they've been routine, but more intermittent than before. So this is an example of how satellites can lead to emission reductions, however temporary. And it also illustrates the importance of continued monitoring. Okay, so let's zoom back out and go to a different area, this time the Permian Basin. The Permian Basin has been a subject of intense scrutiny for many different measurement platforms, including satellites. And these are some examples. On the left, I'm showing Tropomi observations from one pass on July 15th. And you can see there's some high concentrations, but there are a lot of gaps in the image. So we can fill those gaps by looking at temporal averages. The middle panel showing a month of data. And now we can see the familiar hotspots for the Delaware and Midland subbasins popping out. And then, of course, these hotspots are the result of point sources. And we can see those with all different instruments, Sentinel-2, Prisma, GHGSat, and others. And you'll notice that some of these Prisma and GHGSat emission rates are much lower than the ones that I was showing for Turkmenistan, or that we can see with Sentinel-2. But what I really want to focus on here is the middle panel. And what can we do to monitor regional scale emissions, across an entire oil and gas basin with satellites? The way that we do this in general is by inverse analysis of the observations, or by inversion of the observations. And the way it works is that we start with a prior estimate of emissions for a region of interest on a grid. And the example here is a global region of interest. And this could come from a bottom-up inventory. It could be an official inventory from, that a country submits to the UNFCCC. Those emissions as a product of activity rates, like the number of oil and gas wells, and emission factors, the emissions per well. And we use that to drive a 3D chemical transport model, which we can then sample to simulate satellite observations of the simulated methane atmosphere. We can compare those simulated concentrations, predicted concentrations, with the actual observations from the satellite. And the inversion consists in the comparison, adjusting the emissions up and down to better match the observations. And it produces what's called a posterior estimate, or an optimal estimate of emissions on the grid. So an example of this in action was done by Zhang et al. In 2020. They applied this technique to the Permian Basin with 11 months of Tropomi data. They started with the EPA inventory for the Permian Basin on the left, with an expected 1.2 teragrams per year of emissions. And then after ingesting the 11 months of data, they landed on a posterior estimate of 2.9 teragrams per year. So more than twice as much, with clear hotspots over the Delaware and Midland. Now, if you're interested in doing this kind of analysis yourself, you can, because we recently built a integrated methane inversion IMI platform, which is deployed on the AWS cloud for free. And it allows users to define a region and period of interest. The example here is Permian Basin at 25-kilometer resolution for 1 month. The IMI generates a preview of the prior emissions that you're starting from. This example uses the EDF's inventory instead of the EPA inventory. And the Tropomi satellite observations available on the cloud. And then with a single command, you can execute the inversion to get a posterior emission estimate, which in this case is closer to 4 teragrams per year. So yeah, there's a QR code here that leads to the website shown there. And if you're interested, I encourage you to check it out. Now, before I close out, I want to give just a quick preview of some ongoing work where we've adapted, modified that IMI algorithm to estimate weekly methane emissions from the Permian Basin. And this is the basic result. We see on average really high emissions, close to 4 teragrams per year, so higher than previously reported. But what we were really after was the temporal variability. We wanted to understand how the emissions change over time and maybe what's driving those changes. And we see really large fluctuations on weekly to monthly and multi-week scales here. And so we're still, trying to interpret this in terms of economic drivers. And what we can say so far is that new well development and the local natural gas prices in the Waha hub seem to play an important role. We see surging emissions during periods of enhanced well development and crashing local gas prices. So yeah, ongoing work. Anyway, I hope that these examples kind of give a useful overview of the different capabilities we have in this space for monitoring methane emissions. And I want to leave you with just a few key takeaways. So one is The satellite observing system for methane is expanding extremely rapidly, and already it can quantify emissions across a range of scales from global down to individual point sources. Two, we saw an example of how diplomatic intervention in response to emissions detected by satellite can lead to reductions, but also of how routine monitoring is very important. And then finally, looking to the future, a key challenge, I think, is going to be finding new ways to combine information from all these instruments across scales to paint a clear picture of methane emissions, and with the ultimate goal of supporting corrective action. So thanks.
Well, good afternoon, everybody. I hope you're all awake and invigorated after our nice little sojourn outside. I'm glad we planned it that way. So my name is John Goldstein, and I work for Environmental Defense Fund. And I'm really happy to be able to be here and talk with you all today. But I want to make a sort of a caveat at the outset, which is that I am far from a PhD in atmospheric science, but I'm here to talk about the sort of the ways that we're using the work of Daniel and Ángel and others to actually create policy change at the state and federal level in the US, which is what I work on. So very happy to be here and talk about that today. Talked about this a little bit, but just to kind of back up and why methane is important. Daniel mentioned that it's driving a third to a quarter of the warming that we're already experiencing. So for those of us that are worried about climate change, that care about climate change, it's a very powerful lever to get near-term action within our lifetime on climate. But it's more than that. It's also the primary component of natural gas. So the gas that we use to cook dinner, to heat our homes, is mostly methane. So for folks that maybe aren't as enlightened on the climate issue, but do care about wasting energy resources, particularly right now, where we're trying to get our European allies off of Russian gas and find ways to heat their homes this winter. Cutting methane emissions makes sense for them too. It's a win-win. And not to mention the local air quality benefits from cutting methane emissions, since when you cut methane at a production site for oil and gas, you're also capturing the VOCs that lead to ozone formation, the things like benzene that can cause cancer. So it really makes sense kind of across the political spectrum and from a number of different perspectives. So you guys have probably seen this. Satellites discovered this just last week, the Nord Stream rupture in the Baltic Sea. I would venture a guess that were it not for satellites, we may not have found this, or at least not as quickly. I think it was GHGSat and Ángel that helped find this as quickly as they did. And so, here's an excellent example of how satellites are increasing our understanding of what's going on when it comes to oil and gas infrastructure and emissions. And we can use that data to actually create change on the ground, which is excellent. Another great example of this from very early on in sort of the methane satellite era is Skiamaki, which was one of the first, very crude resolution. But what Skiamaki found in the San Juan Basin in New Mexico was the most concentrated plume of methane at that time anywhere in the US. This hotspot was so intense and so striking that the folks at NASA that first saw it thought that the device was broken. They thought, this can't be right. There's got to be something wrong here. But no, it was correct. And subsequent science largely tied that back to problems with oil and gas development in the basin. And that then in turn was an important piece of information that has led the state to enact some of the toughest methane oil and gas rules in the nation. So, I think it's a great example of how this data has led to positive policy outcomes. And I'm going to talk about that a little bit more at the end. So I wanted to dive a little bit into one of these methane satellites that's coming, MethaneSat, which was on Daniel's slide. This is a satellite that is being built by EDF, actually being built by Ball Aerospace on behalf of EDF. and will be up next year. And so we're very excited about it. So I'm going to kind of talk a little bit about that and how it fits into the ecosystem of satellites that are up there, and how they each kind of have specific roles and can sort of create the better transparency that we're looking for. So I'm not going to spend a lot of time on this because I think Daniel covered it, but MethaneSat combines some of the best, or it will combine some of the best pieces of the existing satellites. The ability to try and sort of see pinpoint accuracy, and the ability to sort of see rate over time over broader areas. So that's really, really important to make this data actionable. You want to be able to find where the problems are, and you want to be able to understand the rate so that you can focus in on, those big leaks like Daniel was showing us from Turkmenistan, the big rates over time, so that we can, make sure that we get folks out there to fix those promptly. And that's sort of the chocolate and the peanut butter, for those that remember the old Reese's peanut butter cup ads, of what MethaneSat will be able to do, combining those two things, the tight spatial resolution with the rate over time piece. So, I mentioned this a little bit, but this is important, not only to folks like environmental NGOs like EDF, but this is important to regulators. So this data helps inform where you send your inspectors. It helps inform, where they're looking at. It also helps, obviously, inform industry about where the problems are that they need to go address. And a third really important consumer of this is investors. So we're seeing more and more investors that are, interested in and concerned about climate change, and want to ensure that folks that they have investments in, like oil and gas companies, are doing all that they can to address that. That's a, very, if EDF goes and talks to a large oil and gas company, that's one thing. If their investors go and talk to them, that's another. And so that is another way that I think this data is becoming more and more useful. So I mentioned this, I'll just go quickly through these next couple of slides, but, again, MethaneSat is sort of combining, the ability to see over a wide area with the ability to see the smaller leaks, which is important. This will be launched next year, and that is the plan. And it will be able to, track emissions back to their origin, provide information in close to real time, which is obviously important. We don't want to let these problems linger. We want to get them addressed quickly, and is going to be able to cover the globe. So not just look at specific point sources, but be able to sort of find them, and then other satellites like GHGSat and others can be utilized to kind of focus in on the problem areas that are found. And then obviously important, this will be done at the low price of free. So for data users, this will be out there in the public space. Folks will be able to see it. It'll be totally transparent, which is, different than proprietary data that an oil and gas company might only have access to for their own assets. So that's really, really important. As an environmental NGO, we want that transparency. We want to ensure that everyone can see this data. It's not just going to be available to users that pay a subscription. So I don't want to leave you guys with the impression that MethaneSat is the end all be all. It's great and it's awesome, but it's going to be a tool, and it'll be able to be utilized with a number of other tools in space to get after these problems. For instance, we're going to hear from Ángel in a minute about GHGSat, which will continue to be important, again, at focusing in on those problem areas and getting folks out there. So it's part of this constellation that we're very excited about. and about the ability for it to be utilized with these other mapping efforts. And that's true with satellites, but that's also true, I think, with other technologies of methane detection. So the matrixed approach, where you're using satellites, aerial-based approaches, ground-based approaches, I think is where we're heading. Each one has their pros and cons, but when you combine them together, you're really maximizing the pros and minimizing the cons, and you're able to get the best picture of what's going on the ground. And that sort of matrix approach, using multiple different methodologies for collecting this information, I think is what's going to be happening, and what we're hopefully going to see happening more and more in the regulatory space as folks like the Environmental Protection Agency look to finalize rules that'll contemplate things like these newer technologies. Methane air is an example of that. So this is something that we're flying right now. It's actually a very similar device to what's going to be on Methane Sat, but we're, rather than it being up in space on a satellite, we're sort of testing it with aerial functionality right now. It's being flown on a G7. It's sort of a couple of things. It's kicking the tires, making sure it works well before we put it up into space. But it's also, at the same time, we're collecting data, and that data is incredibly useful. So here again, Daniel had some great slides on this, but this is the Permian Basin. This is the most active drilling basin in the US. And here we are flying and being able to find these problems and focus in on them, down to pretty fine levels to be able to go out and get folks to fix them. And just a couple of brief scientific examples too that are coming up. I was talking with Daniel earlier about all the great papers that I feel like have come out in the last 6 months, and this is one of them. So my colleague Marco Mara was looking specifically at smaller wells. There's been this misconception that we need to have our regulatory approaches be different for smaller wells because we don't want to make them uneconomic and drive mom and pops out of business. And what Mark's paper found is that, one, these wells are by and large owned by larger producers. 75% of them are owned by large, well-capitalized companies. These are not mom and pops. Two, while these wells produce only about 6% of the oil and gas in the country, they're responsible for half of the methane emissions from that sector. So really, really important that we get after them and have them included in these regulatory approaches. And this was a paper that was done not with satellites, but with these ground-based approaches. So again, it's not like we're replacing this, but it's going to be an added benefit. This paper was informed by satellite data. And I think the main thing I want to focus in on here on this JPL study is that, and this is really interesting, this is the first time we've actually seen this. So states like Colorado and California, starting about 8 years ago, put strong methane rules in place. And everybody's been asking since then, well, what are they doing? Are they working? So this was the first time that we actually have some evidence that shows a lower frequency of super emitters in California and Colorado, the states that put the rules in place. It's pretty good evidence that the rules are working. These super emitters are these large leaks, and the best way you can fix them is if you require people to go out and inspect their sites on a regular basis. It's kind of a no-brainer. And so since these states are doing this, they have a lesser prevalence of these super emitters, these big leaks. So that's very important, as we look to try and get something similar instituted nationwide. And that is brings me to my final slide, which is just the sort of the opportunity here from a policy perspective. I mentioned Colorado and California. New Mexico has also very recently, within the past year, put some of the nation's best rules in place to limit emissions from oil and gas development. It's a big deal. People don't realize it, but New Mexico is now the #2 oil producer in the US because of everything coming out of the Permian. So getting strong methane rules in place in the #2 oil producer is a big, big deal and important precedent for what EPA is working on now. Perhaps as soon as early next week, we'll see a draft proposal from EPA that applies to new and existing wells all across the US. The same sort of tried and true approaches that California, Colorado, New Mexico, Pennsylvania, Wyoming, Utah have put in place to try and limit methane emissions from oil and gas development. And it's going to be really important to see how they include things like the frequent inspection at smaller wells, if they include policy approaches to try and curtail flaring, which we heard about this morning is a big source of methane emissions and a big problem, when you can see it from space. I think we ought to be getting after that. So those are sort of from the policy perspective, those are the things we're keeping a close eye on. And hopefully you guys will all join me once those EPA rules are released and, file some supportive comments and testify at the hearing. But anyway, that's it for me. Thank you very much.
Great. Okay, well, thank you. Good afternoon. Thank you for being here. I know we just had these two presentations that is just essentially going to streamline what I'm going to say here. So there are a couple of things that Daniel explained that I was trying to spend some time so that we're getting some efficiencies at this point. So thank you again. So my name is Ángel Esparza and I work at GHGSat. And so one of the things we have been talking about this particular type of technology that we have. And essentially one of the things that we want to do here is kind of approach what the panel is, right? Detecting and responding to methane leaks. So what are we doing, right? So essentially we can have all this science and practices and things that we do on a daily basis where scientists are doing, but essentially we need to take this to action. We need to do something with it, right? So it's approaching the companies that makes the most sense, at least for, in this case, the oil and gas, which is being touted as the low-hanging fruit. So essentially what I'm going to show you some examples here. I'm going to walk you through all of this. But one thing that is very relevant, and listening on the previous kind of the first panel and the second panel. So if we really think that the problems are at the very small leaks, right? Then essentially we have accomplished everything, right? If we're focusing on the very small leaks and that's our own solely problem, that means that the methane issue has been fixed. What I'm showing you right here is what GHGSat did in 2021 with 2 satellites on orbit. So the blue dots represent the opportunities that we took. Basically, we took those emissions or those detections or observations, I should say, and we found nothing. But then the red dots, those are the ones with a detection, with a plume in it. So this is relevant in this sense because what we have here is we're trying to map in the world. So that's one of the things about satellites. It gives you that world perspective. You're able to see how the globe is actually behaving on this. So we have seen all these solar maps from other satellites, which, by the way, all that information is very useful. And GHGSat uses that information as well. So one of the things here, and if MethaneSat is going to give it for free, so more power to us as well, right? So that's essentially pretty good for everybody, for all the community. So essentially, we just tapped this into one of the researchers here. I guess the point here, what I'm going to show you is we measured this with 2 satellites. We look over these particular facilities because these are satellites that we test, as Daniel explained, right? So it's a point source. So we test, we give it a lat long, and we're able to find and look at that particular point. I'm going to explain in a later slide how this thing works real quick. So one thing interesting here is that by looking at the multiple industries that are methane intensive, essentially by using that reference there, we're basically saying that we measure with 2 satellites around 3% of the global coal, oil and gas and landfill methane emissions, only 3%, right, with 2 satellites. So clearly the methane issue it's there, right? Even with the greatest technologies that we have. So small leaks are important, but we need to look at the large leaks as well, or first of all. So this is how these satellites work, real quick. So Daniel did an excellent job explaining some of these concepts. I'm going to leverage on that. But one of the things that we do, once we give a lat long, as is explained right there, what we're trying to do is this satellite, we're able to change the behavior. So whenever we're in that particular orbit, whenever we're approaching that point, the satellites start actually behaving and moving and repositioning in a way
that start taking around 200 images. So think about this. The speed is 7.6 kilometers per second, and we create what we call a field of view. That's basically our standard field of view of 12 kilometers by 12 kilometers. So that means that within 2 seconds, we already passed that area that we're looking at. So we need to start tasking that particular location and be able to get these 200 images. So we're like, right? In less than a second, you're taking multiple images because we want to conform this 200,000 pixel image. That's why that gives us that 25 to 30 meter resolution. Right, so this is one of the things that, you know, previous presentation 25. Well, okay, it's coarse. No, it's not coarse, and I'm going to show you some of those. So still, it's high resolution imagery. Okay, one of the things, the altitude is 500 kilometers at this point, and this is very important. I have it in bold. The threshold, 100 kilograms per hour. This is something that it's basically okay. If you have 1 kilogram per hour, that would be fantastic from the sky, right? Being able to get to that point. Hopefully, we get to that level eventually. But 100 kilograms per hour is the detection threshold, and we have seen last year with 2 satellites, multiple emissions. Now with 6 satellites that we have in orbit, we continue to see a lot of emissions. So we're doing things. We have policy. We have regulations, particularly in the U.S. and Canada. Kind of on the forefront of the European markets, but they don't have a lot of oil, at least for extraction of oil. Essentially, what we're trying to do here is being able to identify what those issues are. So let me give you this example real quick. This is in the Permian. This happened in June. We detected 5 emissions there last June, right? Now, cumulatively, it's 4,742. So this quantification part of it, it's definitely in the great work that Daniel, Varon, and Daniel Jacob have done, basically creating a framework for quantification. But this tells you a couple of things, right? This tells you that you have a plus or minus there, 33% or different. So there is an accuracy associated with it. And so I'm going to explain that with you real quick in the follow, not on this one, but the other one. But this is what we look real quick. And I'm going to make 2 points here. So on the left-hand side, you have the albedo, basically the surface reflectance. I'm showing you this because you see that black spot right there? So that's water. So as Daniel explained, right? So this particular methane, I guess doesn't get, or the technology that we have, we're trying to measure light and how it bounces off the earth or the ground. But with water, it gets deflected and it gets absorbed, some of it. So that's a challenge. And start thinking about the Nord Stream situation, right? We're going to explain that. So off of this on the right-hand side, this is what the methane mask or methane enhancement that we have. So where do you think the emission is? Did you see it? So real quick, it's there, right? So that's the red thing. If we go by that scale, essentially, that's basically the column, and it's in this one is not in ppb, it's in moles per meter square, because we're trying to assess the column from the ground to the top of the atmosphere. What's the concentration in? So as addressing the plus or minus, talking about papers, this is a paper that is still in the works, peer review, or being peer review at the moment. That's the link. What I wanted to show you about this is that how the different satellites and technologies and teams are actually doing the quantification part of it. So remember that plus or minus is that how accurate this quantification is, okay? And so GHGSat ended up being pretty much in a really good position on that particular paper. So I encourage you to visit this. If these slides are going to be distributed, then you have the link there. Let me talk about this use case. This is the Permian. You see all those well paths and everything, right? So that's one image there. So how do we approach customers or potential owners of this particular link? So we have to make so this is essentially, it's not our client, so he's not paying us, but we have this mission and vision of, if we have problems, we really need to tackle them, and we need to, in a way, tell the people and say, you guys have an issue, can you fix it? The reason I'm showing you this is because we contacted someone and we showed that was the culprit. So what they were doing is a blowdown. So not a leak, it's a blowdown. And essentially you have to do those type of events, or if you're in the oil and gas industry, you have to vent some of those things because you have to do some maintenance in some of the lines, you have to do, it's an emergency blowdown, whatever the reason is, and you have those things. So have we seen those? Yes, we see those because it's methane. There is no way to distinguish, oh, that's a blowdown, don't look at it, right? It's methane still. It's just the policy part that doing blowdowns, as long as you ask permission, are, they're acceptable. So that's the part that we need to work on. Another case study real quick. This is the winter of winter 2022, which was the beginning of this year. This is an interesting case. Long story short, it's a brand new facility. They designed the facility. We detected emissions that it cannot be. It is not us. You had a problem with it. Are you sure? Well, let's start looking into it. So they start looking into it and it says, okay, yes, it's emitting from a source that is permitted. So that's why it's good to emit. It's that. Are you sure? What are your levels for allowable limits for emitting? Long story short, yes, it was permitted because the process emits some methane, but not at these levels. So they got notified, and look at the pricing here. So all the savings, the things that they were able to save just on cost savings law and on the gas lost, it paid for itself, right? So we're not NGO, so we don't have anybody supporting us. So it's a commercial business, right? So once you prove the value of this type of monitoring, then companies will realize that it's something valuable to them. Okay, this is hot, very, very hot, right from the news. So remember I showed you that black spot? Okay, so that black spot was water, like that gets absorbed, but the company is basically working on this solution, which is called the glean mode. It's not, it's been used by NASA already and everything, but it's the glean mode aspects of it. So this actually proves that by actually leveraging, even modifying how the satellites actually take that measurement, you're able to detect it. So this is what happened with the Nord Stream 2. So first explosion was on September 26th. We started tasking the satellite whenever we made aware of that. Then we took about a couple of observations. And what happened is that it was cloudy. We couldn't see much. So it took us to 4 days to get one clear sky, and we're able to get that particular leak, which is the one I'm showing you right now. This was 120,000 kilograms per hour. So that's the one image that we received first. But then later on, we receive another image that happened before this leak, and that one happens to be 79,000 kilograms per hour. So that's been the largest leak that GHGs have seen for a single source. So it's a terrible event, but it's bad, but we were able to get to that point. So we have a we're posting this on the news on our website, and several outlets are actually taking us to this particular location. So there are more details about it on it. Another example here, so we have talked about oil and gas left and right, but there are other industries real quick. And I'm going to show you real quick. So this one right here is Poland, it's underground coal mine. On a single image, you have 5 emissions. Okay, these are not pinhole size emissions, right? Then you have this one right here, feedlots. Interesting, in California. On June 15, we looked, I don't have any pointer here, but on that one right there on the left, we detected that one. And then the feedlot to the right on that particular is this one right here on the 23rd. Thank you. We found this one, and then this one right here is this guy right on the next day. So that's a big thing for us, right? To be able to detect that. Now, I'm checking my time. Okay, so as EDF as well, so we did the same thing as it was mentioned in one of the panels as well, the second panel. All this technology can be used and placed on an aircraft. And so we have our own aircraft as well. So now having less atmosphere to care about or to assess, now basically improves our spatial resolution and improves our detection threshold. I'm showing you this is not very stellar image, but there's a story behind it, right? And this is related to policy and regulatory background. So if you are in the regulatory aspect and you're required to do assessments or surveys, you're in charge of surveying this area right here. That's it, no more. You do that, and okay, you're good for the next 3 months or 6 months, depending on your qualification. Right? Well, what this top-down technologies allow you to do is to find this particular, it's 87 kilograms per hour. but that's next to the road, right? And it's been leaking, who knows since when. So these could be underground, small gathering lines that are probably, very shallow, very shallowly or something, and they're there. So this top-down technologies allows you to basically detect that. So all of this, I'm going to show you this spectrum because this is the analytics platform and the way that we deliver all this information. So information that is provided, public information like the one that EF is going to give us or give the world, it's going to essentially enrich all these data sets. Whatever Sentinel-2 is doing, the tropomes, all of that is information for everybody, so we can actually use that and come up with insights. So we have our own spectra system, which outside we call it our analytics system in that sense. So in a nutshell, one of the things that we try to do is, as John explained, right, it's this tier monitoring approach. There is, essentially everybody's saying it's not the silver bullet, right? There's no single silver bullet here, but in reality, it's not, right? What happens here is that we need to leverage all the things that are at our disposal to be able to make a full characterization of the sites and understanding, because everything has a different latency, different times and detection threshold. So what we're proposing here is that, having analytics, GHGSat or any other satellite that allows us to do tip and Q based on data from EF, Tropomi, Sentinel-2, Landsat 8 and 9, all that information that is at our disposal, being able to come up and being able to understand in a more granular way. And effectively, if we want to deploy and make it more refined, then we can deploy the aircraft. So all of these technologies have advantages and disadvantages. But at the end, what matters is this guy fixing it, right? Or a crew fixing the leak. That's what matters. So this is my last slide here. So essentially, next steps. What I have here is, in our case, additional satellites, and I guess in everybody's case, right? Any additional satellites will just give a wealth of information. And now we're going to start characterizing even further what we have. So for future satellites, as Daniel already explained a little bit, so for area flux mappers, essentially, what we're trying to do is that eventually in the future, they will have lower detection thresholds. So technology gets it's going to improve, and they're going to have a higher spatial resolution. So that's what's coming. So any technology is continuously evolving, right? Point sources ideally is that they're going to become intelligent and obviously improving in detection threshold as well and spatial resolution, but also if they can communicate to each other, because now you have constellations. And so if they can communicate and leverage other data and to be able to really, really pinpoint these on time. And so in our case, GHGSat is expecting to expand the satellite constellation to 10, all for methane. And that's going to happen next year. So right now we have 6. We're going to add 3 more in the first quarter of 2023 and another 2 for methane in 2020, Q4 of 2023 and 1 for CO2. So we're going to start with CO2. We have the full constellation of methane, and now we're going to have 1 with CO2. We want to see how things go on that part. So I have a couple of publications here for references. I don't know if this thing's going to be distributed, but I have Varon's there like 3 times. So he's done a wonderful job doing all this analysis. And that concludes my presentation. Thank you.
All right, thank you so much. I'm going to take the moderator prerogative and ask the first question while folks are formulating their questions. There's a lot happening right now with methane policies that Daniel mentioned. That's a key lever for reducing rates of warming, addressing climate change in the near term. What role can satellite data play in policy at these different scales? So we're seeing the Global Methane Pledge, we're seeing Inflation Reduction Act, new rules coming out from the EPA. What role can satellite data play, and what are some of the barriers to using satellite data in these policy applications?
So I think I'll take the first part, which is what role can satellite data play. And I think it can play a significant. So, EPA is looking right now at establishing these, nationwide rules. And one of the things that we're advocating that they do is include approaches like satellites in the what is allowable as far as these regulations go. So, the way these rules have worked at the state level and at the federal level in the past is it puts the onus on the industry to go out and monitor their sites, to check them on a frequent basis. In the past, that has been literally a guy in a pickup truck that drives out with an infrared camera and checks his site twice a year or 4 times a year. With satellites now, we can do that, but from space. And that doesn't necessarily mean you're going to replace the guy in the pickup. There'll still be a role for him. Somebody's got to go out and fix the site. Somebody's got to go out in some cases and actually pinpoint what's going on, what piece of equipment is it that's malfunctioning. But aerial overflight satellites, I think, can play a role in that inspection.
Yeah, I had a couple of comments. So one is that for things like the Global Methane Pledge or Paris Agreement, we need some kind of mechanism to monitor progress. So the Global Methane Pledge, for example, is more than 100 countries pledging to reduce their emissions by 30% this decade. So what's the starting point? And how we know if and when that goal is achieved. I think that some of the satellites like Troponin, MethaneSat, and others can allow us to quantify for different countries what are the total methane emissions, where they're coming from, how they're changing over time, as a way to monitor progress on those goals. Another is, at the other end of the spectrum, the scale spectrum, is the point source emitters, and those can really help identify opportunities to cut more emissions. So if there's a country or a state or a sector that is not meeting 30% reduction or whatever the goal is, perhaps this is a way that you could find either different source types or individual sources that are emitting more than they should or more than expected, and give that information to decision makers to deal with the problem.
So tackling that from the perspective of regulatory aspect, right? So before this, I was doing regulatory stuff, right? So a company they basically abide by what's the minimum, well, I should not say, but some of the companies will just abide by the minimum required that needs to be done, right? So there are a few that they will go above and beyond because they want to do, they have other metrics, other scopes. So one of the things that happen so you can have this regulatory scheme, and let's say it's in favor of alternative monitoring and incorporating satellites, aircraft, whatever the situation is, right? That part is going to take some time because from being enacted and then to be actually implemented. It takes a lot of time. Now, do we have time to do that? Well, it remains to be seen, right? But one of the things is that people or companies or natural people are kind of not necessarily good with change. And so you have people working, doing those in that facility. So let's say if I go, I'm an operator and I go and tell the supervisor to start getting your guys to do a different thing. That process takes a lot of time. So from enacting to actual implementation and do the work, it takes a lot of time. And now adopting a technology, adopting the understanding, making the people understand, or at least they realize that it's helpful. That's the part that it's part of our job, of course, but that's the part that's going to be the hardest, for these people to buy into it. And so we can do all policy, all regulatory aspect, mandate it, but the problem is going to remain. So that's the clear example with New Mexico. They have done this a year ago, and they're still having some issues with some of the operators. But it's going to happen eventually. Change is going to happen. So that's one of the challenges, just to complement the other two answers.
Other questions from the audience?
Thank you for the great panel so far. I'm Paul Grogan from Stevens Institute of Technology. I'm curious a little bit more about the point source imaging modes. Specifically, so Ángel, you mentioned a little bit about the future of intelligent detection and coordination among constellations. what is the current imaging mode for the point source imagers? Is there any sort of coordination across mission boundaries on which sites to image and when, and how to build a larger collective data set? Thank you.
No, that's a great question. So the way we do things right now, so we have, with each satellite, we have a limited capacity, right? So each satellite can keep adding and adding capacity. So it's a matter for us to understand where do we want to devote that capacity. So we have multiple drivers. So one driver is our analytics. If we have that capacity in a particular area, we're in that particular orbit, and analytics is telling us you want to look there, so it gets that connectivity. But the reality is that we also have customers that we need to satisfy, right? So capacity might be basically tasking over whatever the customer needs. So, I mean, we're trying to be smart on that part as well. But the more capacity, that's the reason of deploying satellites. That's the reason of not waiting and to get the next breakthrough and getting to half of what we have in the mission threshold. The idea is to be able to have this full constellation and be able to have enough capacity to have those leverages, to be able to have that particular revisit time, daily revisit time, and be able to get to that point. So that's exactly what we do. So eventually, just tying to that question at that point is, what we're trying to do is make this system smart enough to be able to complement each other, to be able to not crash with or to complement what the other public data sets are there, and be able to get smart about it. Yeah, that's the plan.
Hi, I'm just wondering, what is the spatial resolution of MethaneSat going to be? I'm not sure I heard that.
Daniel tells me it's 100 by 400. But let me check my notes. by 400 pixel size is what we see here on target.
Any questions? Students too?
Hi, I'm Erin. I'm in the EAP program. I'm interested in the regulatory versus industry side, and to say versus in the instance where there might be legal conflict, right? So with comparative satellite data, I'm just wondering if that's coming into play legally, where somebody says, well, we've got this satellite data that says this, and then on the other side, you've got somebody that says, well, we've got this satellite data that says this. How does that play out? And I would anticipate that also folds into the overlay of other kind of data that you can marry that with. But what does that look like?
That's a really, really good question. I think the honest answer is we don't know yet. That hasn't come to pass yet. These approaches haven't been incorporated into regulations, and that I hadn't thought about that, but I think that likely will happen in the future, where folks are saying exactly what you're saying. But we see it here. Why don't you see it there? And so that's going to be interesting to see how that plays out. Going forward.
I can comment briefly, but you probably do a better job. Okay, well, anyway, what I would say is that I think there have been some instances of this between satellite observations and ground-based observations. So an example is that, for example, for landfills with an instrument like GHGSat or Prisma or some of these other point source images, you can see emissions from across the whole facility. And there could be cases where you see maybe pretty large emissions, but the folks, the operators are using ground-based techniques. They can't cover the whole facility all at once, right? So it might be hard for them to miss it, to catch that same thing. But then there can be disputes. Well, okay, these satellite people are saying that we're emitting whatever 5,000 kilograms per hour, but we're not seeing that, so they must be doing something wrong. And I think that the gaps in measurement techniques can lead to disputes, and so it's probably a situation where you need careful validation to convince people that the technology is really reliable.
No, and just briefly here, so no, that's right. So one of the things, just to add into that, right? So one of the things that we are actively doing is precisely, okay, how can we, like, if you think about any process, even ground instruments, right? You have to have some calibration. You have to have, okay, you calibrated your instrument, how often, and each instrument will have their own schedule. So with satellites, it becomes a little bit more difficult because we're not sending people to calibrate things upstairs, right, or up there. So what happens is that we have to rely with control releases to see how the performance of the satellite is. So the more we document that, the more certainty we have that our measurements are correct. So the example of the landfill is it's perfect because that's exactly what happens. Landfills in itself, they could be a little bit like an area source rather than a point source. So you can actually capture that, and that a sensor may just not capture the whole picture at that point. So you can have those problems, but at the same time, you know, that's why we're saying satellites is not necessarily the solely solution. We can just make a different platform. But your question, I think it was, what if you have 5 companies with 5 different satellites, and you say, okay, so who's the one telling the truth? So I think at the end is going to be, so by the way, sort of changes, it could be changes within the same source. It could be variability there and all of that. So if you have 2 instruments measuring one next to the other one, there still could be a variability on the quantification, let's say, or in the detection. But that's going to be interesting. It remains to be seen because we don't have that. At the moment we have more players, that's something that we definitely, the researchers will be doing that kind of research, right? And we're going to start, okay, like kind of the one I have here on an accuracy. Okay, so let's do that for all the satellites that we have and see how companies are lined up. So it's a problem that we're going to have. It's a good problem to have in a couple of years, I'm presuming. So that's a great question. Thank you.
Follow-up question on that. How do you think about communicating uncertainty in these measurements? Because it may be that actually these different measurements are all within uncertainty bounds with one another, but that might not be what a company or what a regulator is looking for.
So what we're talking about?
Okay.
Okay, so the uncertainty is always a very touchy aspect when if I go and talk to a customer and say, hey, wait a minute, you're getting plus or minus 40, so what's that, right? And it's like, oh, okay, hold on your horses, right? So what happened here is that that uncertainty in itself is associated with the quality of data that we have to make that calculation of that emission rate. And so I'll give you an example. So if we have wind speed data that is from 3, we have a measurement from 3, and then another measurement 3 p.m. and another measurement for 4 p.m. And the emission happened at 3:15. Which wind speed do you use? So and which direction do you use? So there is uncertainty already there. So the reason that we're trying to do here, just to go back to that particular paper that is in process of being peer reviewed, that's exactly what it was assessing. Tell me what is your best guess or your best calculation, and let's see how it compares against the ground truth. And essentially, we provided that with our plus or minus of, let's say, 40, 30, 20%. But the whole point is that calculation, how aligns is what matters. So in our case, we did great on that particular test. No? So the idea is to kind of test things like that. So that's a very touchy aspect when I go to an operator with that. Of course, yeah, that happens. You want to say something?
Yeah, I got something. So as I was saying, a key source of uncertainty in this quantifications is the wind. It's actually the dominant, by far, the dominant source of uncertainty, and it can easily give rise to a 50%, error. So we do need these careful validation studies to really test. In that case, I think there was even a version where they gave wind speed measurements taken on site and said, okay, so like you did your first try using those like meteorological databases. Now here's the wind speed that we actually measured next to the source. Try again, and then finally they kind of release the ground truths. So wind speed is a major problem, but what can help is temporal averaging. So if you have many observations of a source, even if it's variable, and the individual observations are highly uncertain, you can get a pretty solid estimate on the time average behavior. Now, a final comment is that a lot of the time, the exact value of the emission isn't the most important piece of information. It's more just that there's a strong emission, strong enough that we can see it from space. So whether it's 1,000 kilograms or 1,500 kilograms per hour, in some cases, it won't really matter.
Daniel just stole exactly what I was going to say, which is that from a regulator perspective, and I'm a recovering regulator, it's really more of a presence versus absence issue. So, if you can see it from space, you ought to be able to go out and fix it. And quantification is important. I don't want to downplay that. But, as far as getting these things fixed promptly, and we have to consider too that, what this is competing with right now are the guys in the pickups with the infrared cameras. They're not getting quantifications. They're going out and they're seeing a leak and fixing it. And so, if that, when you're comparing it to that, it's, it's a very similar.
Say one more question. Oh, I was saying I will. Oh, you go here and then here.
Hi, I'm Bailey. I'm also an EAP student. This is maybe just a broader question as people who work in the space of methane versus carbon, because I think a lot of times when we're reading the general news stories about climate change, we're talking about decarbonization. We're not necessarily concerned. I mean, for a long time, natural gas was being touted as clean energy source. So I'm just curious how, as like methane professionals, you go about having these conversations with maybe people who are not as well versed in thinking about methane as dangerous as it is.
Yeah, I think all three of us really hit on that, and that is, communicating in the time scale, and understanding that, addressing CO2 is incredibly important. But if we want to bend the curve on climate change within our lifetimes, methane is really the most powerful driver in which to do that. And so it's not a question of either or, it's a question of yes and. Also, I often find working with industry, the economic issues like Ángel talked about, going out and fixing that leak paid for itself because that's more product that they have to sell is incredibly powerful too.
No, that's an excellent question because so we need to work with what we have right now at our disposal. What makes sense right now. So that's why the natural gas is being touted as the transition fuel, right? So already has that label that it's going to end essentially. Now the timeline and when that's going to happen is, you can have projections. The thing is that there's a lot of reserves, a lot of reservoirs still. There's a lot of interest. Look at wars right now, right? I mean, there's still a lot of things going on around that particular situation. So decarbonization, in a way, if it happens, but on the humanity level rather than the industrial level, I think that's a good progress towards that, right? But it's just going to take time. It takes generations to get to that point. To shift the whole thing, just if once we want to change into lithium or batteries and whatnot, then we create that other problem, right? Like if you want to get a vehicle right now, supply chain, logistics, and all that is so problematic. So we're getting a taste of what's going to happen. We want to do a drastic change like that. So I think right now, for the time being, what is going to be very important is to focus on doing what we're doing right, while we slowly but surely get the right solution for that transition. But eventually, we're going to get out of the natural gas. That's my take. But even with the combustion, right? How can we get more efficient in the combustion? As simple as that. And there is a very interesting now push for flares and how they're doing and how the combustion of flares has been touted as 98% efficiency when in reality is showing 90% efficiency. Now or 95. So those 3% change essentially, it's creating a big impact. So that means that the other 5% is being emitted, right? So of all the flaring activities, there was one map right there that it was showing in the Nigeria area. It's constantly flaring. It's incredible. So there are many other breakthroughs that, just to sum it up, that can happen to kind of continue using this resource in a more efficient and intelligent way. And then eventually that transition is going to occur. That's my take.
I mean, I would just kind of echo what John said about the time scales. That's the way that I think about it. That, you know, CO2, I do think is the most important greenhouse gas for us to cut, because on a longer time horizon, it's really what's going to control the temperature. So if we go after methane without going after CO2, it'll be good for, you know, the next 10, 20 years, but then it'll catch up to us and we're in big trouble. So I try in all my, you know, presentations and conversations about this to always say, okay, CO2 is super important, but, you know, the key attribute of methane that makes it special is that short lifetime that John said, kind of we'll see benefits right away, or within 10 years or so if we cut those emissions. So that's why, you know, it's a major priority right now to reduce the emissions from the oil and gas sector. You know, we may need to use natural gas to, you know, for fuel for a while. So let's make sure that we're emitting as little as possible and actually be able to capitalize on some of the CO2 gains that we get from using a fuel like natural gas rather than a fuel like coal.
Hi, thanks for the talks. I really love them. That's very exciting. So where I work with other air pollutants, for some federal and state agencies, there's a lot of enthusiasm for satellite data. For others, they don't have the capacity or the time to really bring it in, or they have skepticism because it's not on the ground data. I'm kind of curious from your perspective, how do you see regulators, do you see them taking this up and making it really a part of what they do, or do they kind of see it as like, this is some extra thing, and what would it take to get it more incorporated?
I think that, I mean, every state's a little bit different. And, you know, then you've got the federal overlay, the Environmental Protection Agency over all of that. But I think that to generalize across all of them, I think they're always looking for better, faster, cheaper ways to do their job. And I think the forward-thinking ones recognize that satellites are that. You know, they're providing tools. They're not going to replace, you know, everything, but they're another sort of tool in the toolbox that they can use. And you know, the state of California, for instance, is launching their own satellites for that very reason. Yeah, I think that it's really fast developing in terms of, you know, regulators understanding the power and the efficacy of like these tools.
Get out of my wheelhouse.
States. So yes, so one of the things, so I'm pretty sure you all are aware, right? So the federal level will set the minimum standards of doing stuff, right? Or doing things. How do we want to operate? And then states have the liberty of going at the same level or do something else, right? There are some states that are more progressive, and then there are other ones that they don't want to have this air, right? So they don't want, they're in denial, of course. So it's a matter of what we do is if we want to be very effective at passing all these levels through the state. So we need to start with the federal level, buying into that technology. So you have other institutions that advise the federal level, in this case, the EPA. So you will have NASA, for example, right? It will advise in a way, be one of the advisors saying, okay, you can trust in that. And then once the federal level understands that there is a way or an avenue or the usefulness, which in a way they do, but we still need that extra jump to get it to that level. Then they set the minimum standard, and then essentially will trickle down to the states. And also you will have states that, okay, I'll venture and do more. And so we can essentially try to see how can we collaborate and help, and they can leverage all the information that is available. And that's a good step in that direction. But right now, the way I see things, we're in that transition. Nothing is necessarily said like, okay, satellites are going to help us out. I think we're in that process, and it's our job and the scientific, the regular, to convince that there is there is an opportunity with satellites, and will be your job, I guess, if you are part of this program as well, right? The energy policy, right? So essentially to convince what's the utility of this and how can we basically help with this type of problems. Because right now it's methane, but it can be used for other things, right, as well. I mean, depending on the satellite.
Yeah,
We're at time. Okay. Thank you so much to our speakers, and we'll